Hello everyone, and welcome back to a new episode of Silicon Zeros. I did a little poking around off camera. I did a couple of things. One thing that I did was I solved multiply. We'll get to that in a minute. I just didn't really want it. It was going to be like a whole long thing of just the algorithm is clear, but just like getting it all wired up was going to be complicated, and I didn't really want to do it. And I did like some thinking about alternator and threes, because like alternator, right? It seems like every part here we have is absolutely essential, and yet we're at 8 modules out of 6. We can somehow dispense with 2 of these, and I haven't really figured out how at all. So like I did a lot of thinking, but I didn't really come up with anything good. I was thinking about stuff like trying to somehow reuse this counter as part of this thing, but I couldn't see a way to do that. I thought of some kind of weird stuff, like instead of add 1, subtract 1, I could like add 2 and then don't add anything. Wait, that doesn't work. I don't remember. There was some nonsense about 2s, and I even had some thought about like, well, maybe over for the counter I could have it go up by 2 and then down by 1. And like, then I would write a 0 and then a 0 and then a 1, like, and then up 2. Like, there's different ways to traverse this input. It doesn't have to be scanning linearly. And so maybe having this counter go in a different order could enable a simpler solution here, but I couldn't figure it out. I also thought of sending like the output of this counter into this cycle somehow, but anything that we're writing from here every cycle into this 2-cycle periodic thing is just going to be a delayed version of this, I think. So I don't know, I couldn't really come up with anything. But one thing that, like, I was thinking about it because alternator was an important part of how I solved 3s, and also how I solved something else. Oh, faux reg, right? Yeah, I have an alternator up here, and this one we're off by 8 modules, and I was like, well, okay, we're using an alternator, so maybe if we could find a way to make that smaller, then we could get a little closer here, but I don't know. There's still something I'm doing drastically wrong here, and I don't know what it is. Pleasing Fungus actually did suggest that I reread the description of this puzzle next time I'm here, and I haven't done that yet, so let's see what's going on. I've been thinking about a little toy, a machine that reads the numbers stored in memory slots 0 through 3, and writes them to the slots specified by memory slots 4 through 7. Oh, and then there's more words. Were those there before? Or, because I know that he updated the game yesterday. And it might be after I solved this puzzle? Or did I just, like, read the part in red and then skip it because the red is always the important part? I know that, like, sometimes there's stuff in green. I don't know what the green means. But anyway, I just, like, completely... If this was here, I completely ignored it. Maybe it's new. I don't know. So that's interesting. At most 1 latch... Well, I have 4. Okay. All register inputs connected to selectors. Yeah. Do I even have... Oh, wait, no. This is a register, so I only actually have 3 latches. Connected to selectors. And at most 10 modules. At most 1 latch. No register inputs connected to selectors. And at most 10 modules. So he did mention to me a small hint on the 6 module solution, which is that you can do it with no register inputs connected to selectors. So that's something to think about, I guess. But maybe I could devote some time, probably not right now, but eventually to like seeing if I can follow up on any of these. But that's not what I want to do this episode. First I want to give you guys a tour of Multiply. Which is large. I think the largest one I've had to build at 21 modules. I only missed by 2, the ideal solution, which is not too bad in such a large machine. But let me explain to you guys how it works. I actually labeled some of these in case I needed help debugging, although it turned out that, like, I don't know if it was on the first try, but maybe there were a couple of trivial miswiring stages, and then after that the algorithm just sort of worked, which was nice. I didn't have to debug it. So the idea is our counter goes up by 3 instead of by 1. So that's what this 3 here is all about. But it only does so if we're done multiplying the values at this step. Or, well, really it's if we're done reading these numbers. So I think that there's definitely some improvement that could be made in how I advance the counter, because I advance it sooner than I would like, and as a result, like, there's some subtraction and some latches that I have to do that, like, I wouldn't need if I could arrange to increment the counter later, but I have not figured out how to do that yet. So what is the general flow of data through the system? This counter is the base address of the first number we're reading, and we read it. And output either the number we just read or 1 minus the number's old value. So this latch is where we're storing. It's called latch 1. I guess I should call it X, right? And call this one star X. Kind of like I did here. Star Y is the memory address. Y is, I don't know. This is a little bit. I don't have consistent naming conventions, but so this is where we're storing the first value, and that's the one I'm choosing to decrement. So it's this number starts as 7 and gradually decreases to 6, 5, 4, 3, 2, 1 until it's 0 again, and then we're done multiplying. Every time we decrease this number, we add the value in Y, which is the second number, to the latch holding our accumulator. And so each of these latches, we might need to write 2 different things to it, and so each one has an input selector. Basically, whenever this hits 0, we say, okay, I need a new number to multiply, because we're done with the old one. And what that does is it resets this to the value of the first number. It resets this to what? Where is this coming from? Oh, nowhere, of course. So in the 1 case is when you reset. So it resets it to the value we read from memory. This latch is one that I wish I could do without. If I could just read directly from memory every time, it would be much simpler. I wouldn't need the selector, I wouldn't need this latch. And so these are 2 modules that I feel like I could remove if I could figure out how to fix when we increment the counter. Because we're just reading the value and saving it. And we have to have a latch for that and a selector to stop us overwriting it, because while we're multiplying the numbers 0, 1, and 2, this base address is pointing at 3, and so we need to not read what's at address 3 plus 1, but what was at address 0 plus 1. So that kind of stinks. And then here, this is the value we're adding Y to. So when we detect a new value, we have to set this to 0. So it starts at 0, we haven't added anything to it. And then each cycle where we're not done with the multiplication, we add the current value of the accumulator to the saved value of Y and store that back into the accumulator. Meanwhile, we're just writing to the memory address every time as well. Which is what exactly? It's base minus 1? Yeah. So here also, it seems like we could maybe somehow make do without this latch if we could write and read the value in base -1. Maybe that one we actually can do without. Because... Okay, so how does this currently get initialized? It gets initialized to 0 when our thing is 1, right? That's where this goes. It goes to a... No, it gets initialized to, yeah, 0. And then in the other case, it gets initialized to a latch. So we don't actually have any reader for the address that we're writing to, right? Oh. So... I see. I could do without this latch by reading directly the value that we're writing, right? Very nice. But that would just be taking out this latch and replacing it with a reader, and that's all. If this value were initialized to 1 for us, then we could do better by not bothering to reset it and just always read what's there. But it's not, so tough luck. Okay, well, so anyway, that's the tour of Multiply. I'll let you guys watch it a little bit. Just let me get the mouse out of the way there. So you can see, let's see, actually, let's back up here. We're first being asked to multiply 7 by 2, which means 7 times we're going to add 2 into the accumulator. And so you can see that the base, no, x is currently 0 because it is a latch and they're always starting at 0, which means that the values we are now reading from memory are part of a new number, not part of the previous number, and so we save them all. And then in the next cycle, this selector has gone to 0 because what was here is not equal to 0. And now all these things are doing the computation step instead of the load step. We're subtracting 1 from this, turning the 7 into a 6. We're... What are we doing here? Input selector, 9. Oh, we're just not writing to this, yes. We are reading the 9 that's part of the next puzzle, or next multiplication, but we're not using it, we're just throwing it away. This is staying as 2 indefinitely. And then here, our computation step is to take the 2 that was here previously, or no, take the 0 that was here previously, add 2 to it, and then store it again. And so, ta-da! Now we're saying, what is the result of 2 plus 6 times 2? And then we say, what is the result of 4 plus 5 times 2? What is the result of 6 plus 4 times 2? And so on, and eventually we simplify until the first number becomes 0. We write this, and we go, this selector flips to 1, and we're reading all the values at the new base again. Right, very nice. And we could go through this, but it's all quite slow, so there you go. We're done. Wonderful, wonderfully done. I was not sure it was wise promising this to the client, but Jack was right after all. What a wonderful man he is, so clever, so wise. Are you not glad I hired him? This is, of course, we've done some time travel back to board 1 before we were betrayed by Jack. So that was a tour, I suppose, of Multiply mostly in this episode. And let's do an aside or something? I'm interested in these things, but I'd like to at least look at some of these 4s and see how hard they are. Alicia wanted me to build a machine that executes greater instructions for her work. I was busy and it seemed like a big challenge, but after she left for the day, I started to wonder, perhaps it's doable after all? So, the only kind of instruction that we get is greater. And what does greater do? It sets memory slot 10, that's dest, to 1. If 2, okay, so the source and dest are literals. Okay. And we don't have to worry about Militics, we just have to worry about modules. So this is, I think, actually going to wind up looking a bit like multiply, because we... Okay, let me just double check what modules we have. Yeah. Okay, so equal is the main kind of interesting one we're going to have. Also, wait... We only have an adder. I was expecting a subtractor. So that we can subtract them both until one of them becomes 0, and based on which one it is, do something clever. How would you do this with just adders, though? Like, obviously you can subtract a constant using an adder by just getting a constant negative number. So I can... Oh. There's the answer, idiot. Add -1. Okay, so that's how you get a subtractor. Fine. But actually there's another problem. What if they're both less than 0? Right? Does that ever happen? Yeah, it totally does. What's the largest number we ever get? Because we could add like 100 or something, right? Actually, it's kind of hard to do that because the largest number we're allowed to create is 16. Now, you know, we could add together a lot of 16s and get a particularly large number, add it to both of them, and then eventually subtract. But that sort of feels a bit like cheating because it sort of only works for numbers that are not so negative that this is a problem. Whatever large constant I choose, I can only handle negative numbers that are not more negative than my large constant is. So that doesn't really seem like a promising approach. Okay, so you could actually, you could handle this, so, okay, you could try subtracting 1 from each of them forever until one of them reaches 0. And as long as at least one of the numbers is positive, I was going to say, as long as at least one of the numbers is positive, that would give you an answer, right? But when, like, even just look at this very first number, we would subtract 1 25 times, and then we'd say, oh, source reached 0 first. Therefore, source was smaller, but that's not true. Target was smaller. And so I was thinking, if that were true, then we could do this sort of in parallel, where we subtract 1 from each of them, and if that reaches 0 first, then we declare a winner. And additionally, add 1 to each of them forever until one of them reaches 0. And if that wins, then we say, oh, well, one of them must have been negative. But since we don't have a solution for when they are different signs at all, that's not very exciting. It doesn't seem promising. Now you could do 4 copies of this in parallel, right? You could say, I'll try adding 1 to source and subtracting 1 from target. I'll try adding 1 to both. I'll try subtracting 1 from both. I'll try subtracting 1 from source and adding 1 to target. And whenever something reaches 0, I'll declare victory. But that doesn't really work. And I think this needs the same sort of complications that Multiply had, where the input, where you have sort of a loop that is distinct from your read loop, because in order to do the operation, you have to take an unknown number of ticks, and so you have like input selectors that tell you when to reset your inputs and so on. All in all, I think too complicated to do in this episode. I might solve this one off camera as well. I feel like these really hard ones are just like not great for solving on camera. And I don't know, so I probably won't do it. I'm not going to do divide, I can tell you that right now. I've done divide enough times in games like this. It's way harder than multiply. And I'm still glad I did multiply off camera. Okay, but we have a little bit of time. Let's have a look at micro CPU. We glanced at it before, but I don't remember what the deal was. Okay, instead of using a reg file, it has an implicit single register, the accumulator. Right. Okay, so we have load, add, and save are the three kinds of instructions we need to deal with. Okay. That seems pretty simple, actually. So let's grab this. We don't need any, like, weird clock shenanigans. We can just execute each instruction in a single stage because we don't have milliticks to worry about. And we can always, we don't need any latches or writers as part of that, so great. So what do we need first? We need a reader, reads an instruction, and then an input decoder. This gives us a thing. Now, what are these three things? Interestingly, the three instructions all have different sets of arguments. So I believe I don't need an operation selector at all. I can just sort of implicitly, whichever instructions we're not executing, they'll get a nil, and they won't do anything. It'll be fine. Okay, so we need, obviously, a register with one thingy. And this always starts with loadac, so we don't have to initialize our register to 0 or anything funny like that. I guess we kind of do need an operation selector, because while these three inputs are distinct, there are still two of them that write into here, right? We need to choose whether we're writing this or this. We can't just wire them both in and say, oh, whichever one is non-nil, use that. We need the operation selector to let us demultiplex. Or maybe it's multiplex, I don't know. So let's just wire that up to there. In case it is a load, we'll send that in nice and easy. If it is... no. This. If it is an add, then we'll take this and this and then save that. And if it's a save, we don't need to worry about this at all. We'll just send nil. So let's take a writer then. That is fed this and this. I think that's all, right? Seems okay. Let's see what happens. So in this first step, we're saving a 93 in here because it's a load act. That's what we're supposed to do. Fine. Now we're ready to write a 93, but we're not executing a save, so it won't happen. Instead, we're adding. We say add 4. And it's not the thing in memory address 4, right? No, it's self and 4. Wait, what? Should be 6. Oh, the value from memory slot 93, not just the thing. Alright, fine. Oh, gosh, I hit escape again. Alright, so we don't want to wire this up directly. Rather, we need another reader is all. No, come back. Alright, just take this, put it down here. Give me a reader connected to... send it into this add and make it read source? Yes. In fact, we'll do this. There we go. That should address the problem. Oh, no, I fixed the wrong thing. This should be wired up like so. And then sent to here. The output of this adder goes directly here. So it's, if we're doing a load, we're loading from memory. Adders don't touch memory. Okay, try again. So we're storing a 2. Then we're ready to write a 2, but first we need to add 4 to it. Now we have a 6, we're writing a slot 91. And then we're loading that 91 back into the register. What a dumb instruction. Fix the compiler on this one. And saving it again. And then we're saving it... Wait, what? Oh, whatever. The number 2 is there. I'm not sure why. Oh, because that's what was at address 93 for us to read. Okay, fine. Fun little design. Doubt it has much potential, though. Who'd go to the trouble of using a CPU this simple and crude? I was a little worried earlier, but I feel much better now. I don't think we have much to worry about from China when it comes to computer manufacturing. Good joke. Alright. Well, how are we looking on all of this stuff in 4? Fast 2-2. Obviously don't want to do that in this episode. I'm just trying to figure out like what I'm going to do in the next episode. Should I try to cram another aside into this one? Sure, I'm interested in load CPU. Looking at the Aerith CPU today, I thought of a simple improvement I could make. Not a big complex speed up, but just adding the ability to load data from memory. Seems like that would make it a lot more flexible, wouldn't it? Execute all instructions. So wait, isn't this just micro CPU, which had us load values from memory, combined with this? Like, let me just grab this guy. Load CPU. Woo! It's always bigger than I expect. That's what she said. So we just need to add. We have. This is like when we added jump, right? I think we have load and save, which did we have those before? I don't remember. Yes, we had save. We didn't have load. So all we need to do is add support for load. Where would it go? It goes here, because it's about writing. So we currently do not have a load, correct? Correct. Okay, go back. So I just need to, like, make a reader, put it, I don't know, here, connect it to load, and make its input source be, let's see, I kind of need a different reader as well, one of these guys, not reader, input selector. Maybe I don't. Let's see. Where we load from targ. And so save is reading from source. This is reading from target already. So I believe that we can just take this register and wire it up to our reader. This always reads from target. Which means this will always read the value in the memory address pointed to by target, and we'll always send it here. And in the case that we are executing a load, then we will write it to dest, which is correct. So I think that that's fine. Let's see what happens. So of course setr still works fine. What happens in load? Set register 1, yes, to the value from memory slot specified by register 0. Right now register 0 is 7, so we should be reading what's in 7, that's 21, and storing it into register 1. That's correct. Okay, so looks like that was it. We just had to add one module and a couple of wires. Nice, a machine that can both read and write memory should be much more useful, I agree. Reading and writing. When I was just learning to read back in school, I wasn't very good. They tried to be nice about it, but I could tell my teachers thought I was a little slow. It's been a long time since anyone called me stupid, but working here, sometimes I wonder. Imposter syndrome strikes again, huh? Everyone you're working with is so smart you feel dumb, I guess. It's easier to see inside your own heads than everyone else's, though. Easier to judge yourself for the things you don't know. Okay, so I think that we are done with this episode. What did we even do? Did we solve any puzzles? I guess we just did a tour of Multiply. We solved a couple of asides, and we looked at Grader and thought about it for a while and decided it was too hard. So, great, very exciting. Thanks for watching, and I'll see you next time.